Hey guys, welcome back to my channel. Today I wanted to go over the aggressive cows problem on the SPOJ website. It is a great programming problem to practice, especially if you're doing coding interviews or competitive programming contests. It's one of the most highly rated problems on this website, and you'll definitely learn a thing or two after solving this problem. And this video is a little walkthrough into how I kind of solve this problem. But before we begin this video, if you do like what you see, if you do like the content I'm providing, go down and smash the subscribe button. Hopefully you'll enjoy the future content I make. And also give it a like if you do learn something from this video. Without further ado, let's go into the problem statement for this question. So Farmer John has built a new long barn with n stalls. The stalls are located along a straight line at positions x sub n to x sub n. His C cows don't like this barn layout and become aggressive towards each other. Once put into a stall to prevent the cows from hurting each other, FJ wants to assign the cows to the stalls such that the minimum distance between any two of them is as large as possible. Now that's the important sentence there. FJ wants to assign the cows to the stalls such that the minimum distance between any two of them is as large as possible. What is the largest minimum distance? Here you can look at the input format and also the output format. But the important part of this question is this last question. What is the largest minimum distance? And it can seem kind of confusing because there's like two opposite words, largest and minimum. They're kind of contradictory, but the best way I can explain this is in layman's terms, how can you evenly spread out all the cows in the available stalls? That still might not make sense to you, so let's just go over some test cases and maybe you'll have a better idea. Hopefully you'll have a better idea of how to go or approach this problem. So here on the left side, I have our very first test case. If you look at the input cases, there are 5 stalls indicated by the first integer in the second line, and 3 cows indicated by the next number after the number of stalls. So here, if you look on the left side on my Microsoft Paint, we have to place 3 cows in any of these 5 stalls. So for example, just picking some random stalls, 1. If I place cows in stalls 1, 2, and 9, we get a distance of 1 between these first two cows, because 2 minus 1 is 1, and a distance of 7 because 9 minus 2 is 7. Now if we look at this test case and where we place the cows, our minimum distance between any 2 cows is 1. And now that is the minimum distance, but we want to find the largest possible minimum distance. So we can do a lot better than a lot better job of distancing these cows from each other than having them right next to each other with a distance of 1. So let's go down to this second part here, the second line. The optimal placement of these cows would be at 1, 4, and 8. Here the distance between 1 and 4 would be 3. 4 minus 1 is 3. And here it would be 4 because 8 minus 4 is 4. And here the minimum distance here is 3. And clearly 3 is larger than 1 here. And therefore this is the optimal solution. There is no other better way because if we read on the right side here, FJ can put his 3 cows in the stalls positions at 1, 4, and 8, resulting in a minimum distance of 3. So that is the actual answer. Some might argue that you can place the 3rd cow in stall 9, but that really wouldn't matter because the distance between here would be 5, and the minimum distance is still 3. So that was a mouthful. Take some time to reread the test cases and read the problem statement over and actually absorb what is going on in this situation because it is kind of confusing. Pause the video, do what you need to do to understand the problem statement, and come back when you are ready. Okay, once you have read the problem statement and you understand what it is that we need to accomplish, let's go over the concept, the solution concept. So if we look on the right side, it clearly says that we should be using a binary search to solve this problem. And Usually we use a binary search when we are trying to find a specific value within a range. And now you might be asking, what is that range, you ask? The range is, the continuous range is from 1 to 8. And I got these numbers because the minimum distance between any two cows must be at least 1, because like I showed you in the previous example, we had one cow here and another cow here. The minimum distance is always going to be at least 1. And the greatest possible distance between any two cows will be 8 in this scenario, because we have 9 on the very right and 1 on the very left. So 9 minus 1 is 8. So within this range are a list of possible values that might be our solution. We just have to find the most optimal one using binary search. So with these two values, we can say our low variable is 1 and our high is 8. Then our mid will be around, I think, like 4. Yeah, it'll be 4 because 9 divided by 2 is 4.5, but the decimal is truncated. So anyway, the middle is 4. And now we have to check if 4 is a valid largest minimum distance. So the way I wanted to check this is simply by going one by one and checking if there are enough stall spaces so that the C number of cows can fit in all the stalls. So let me just copy these numbers and we can test them out. So we can what I plan to do is always have a cow sitting in the very first stall, because why not? It's not bothering anyone. Then I want to check for the next stall that is at least 4 spaces away. So 1 plus 4 is 5. So we need to look for a stall number that is greater than 5, and that is over here. And now we have 2 cows placed. The next one, the next stall that we should be looking for is 4. The next stall that we should be looking for is 12, because 8 plus 4 is 12. But unfortunately, there is no stall number that is greater than or equal to 12. So therefore, 4 is not a valid answer. That means this answer is too big, and we need to look at a smaller in the smaller left half of the range. So after this, we would move down to low equals. Let me just change the color. Low equals 1 and high equals 3. Then our middle will equal 2. Mid will equal 2. And we can do this process once more. I'll just write them this time. 1, 2, 4, 8, and 9. We'll have our first cow be placed in the first stall. 2 added to the first stall would be 3, and 4 is the next number that is bigger than that. And also, the stall where we place the next cow has to be at least 6, because 4 plus 2 is 6, and that is here. So here we were able to place 3 cows, but we might be able to do better. So we want to look for the next largest possible value. So we would have to look in the right half of the range. So our new low variable would be 3, and high would also be equal to 3. And therefore our middle value will also be equal to 3. And using the same process again, 1, 2, 4, 8, 9. The first cow will be placed at stall number 1. 3 spaces away from 1 will be 4, and here we have a value of exactly 4. The next stall number would be 7, and the 8 is the next greatest number next to 7. So we place a cow here, and now we see that the largest minimum distance between any of them is in fact 3. So that is how we solve it. That was a pretty lengthy explanation. And now let's go into the implementation of that. My explanation was kind of lengthy and it was kind of in-depth. Make sure you understand the concept and the solution concept before moving on to the implementation so that you don't get lost. So if you look on the left side, I have a little template for me to start coding. In the main function, I just have a simple input and output function that will let me take the cases, and all we really have to worry about is what's located in the solve function. So here I have a vector of, or an array of stalls, an integer with num cows, and an integer with num stalls. This can all be found in the test cases located on the right side of the screen. So the first thing that we want to do is sort the vector, because they are not given to us in order. If you look on the right side, it gives us 1, 2, 8, 4, 9, which is clearly not in order. So let's just quickly sort them. Stalls.end. And as I said before, we want to use binary search, so let's make our low and high variables. And now our high variable is pretty much the last element of the stall vector. Stalls vector, so we want to do something like stalls, or no, I'm sorry. The high variable is the difference between the last stall and the last stall and the first stall. So something like this will do. And now we have our low and high variables. What we also want to do is create a variable that will save the largest minimum distance. I'll call this res, and I'll make it to -1, just to make sure that if there is an error, that the answer will be -1. So now we can begin doing our binary search tree. Very standard. I'm assuming all of you guys know how to do a binary search tree. If not, you can always go to other YouTube videos for in-depth explanations. But here we are here to solve the problem, not to learn binary search. And now I will set my mid variable. Oops. Sorry, my typing is kind of bad, but now we have to do the checking whether this middle variable is possible. The way I did this was having a variable called cows placed equals to 1, and the reason why it's equal to 1 is because, as I said earlier, we're always going to be able to place at least one cow down at the very first stall. So we always place one cow down, and we want to keep on placing cows down until either we place all the cows down in their stalls, or whether there are not enough spaces for the cows to be placed in. So I will make a while loop with on the condition that the number of cows placed is less than the number of cows that are actually existing, or yeah. And we want to keep on checking. We want to keep on placing cows one by one. So the way I did it was I used the lower bound function. And the lower bound function is a method that finds the next number in an iterable list, that finds a number that is that is greater than or equal to the number given. So it'll look something like this. Before our while loop, we have to actually create an iterator, and that looks something like this. end, now we're able to use our lower bound function. We'll set our iterator to the lower bound of from it to stalls.end, and we want to find the stall number with the next stall number where we want to place the cow, and that will be equal to the value of the iterator, and plus the middle value, which represents the minimum distance that we want to jump. If for some reason, if there's not a number that is greater than or equal to whatever value was put in here, then iterator will equal to the end value. If this case happens, that means that there are no more available stalls to be placed and we need to break from the loop. If not, then our cows placed shall increment. After this loop has ended, we want to check if the number of cows placed is the number of cows that actually exist. So if cows placed is equal to num cows, that means we were successful in placing all these cows, and we want to look for greater numbers that are possible. So we want to make low equals mid plus 1, and we also want to save this possible value in case that any greater value will not lead to a solution. So before here we set a variable called res. Let's make that res value our mid. Let's assign our res value to the mid value that we can return later. If the number of cows placed is less than the number of cows, that means there's not enough space. Oh, I forgot my parentheses. Sorry if I'm losing my train of thought. It's kind of difficult to do multitasking, but hopefully you follow along. If this condition is true, that means the number of stalls available has there are no more available stalls for the cows to be placed in, and therefore our minimum distance is just too large, and we have to look for smaller numbers. So in that case, we just do high equals mid minus 1, and that is our binary search completed. At the end of this, we can just return our res value. And hopefully this will all work. I'm praying so that I don't embarrass myself. Okay, so I have to change this to the Windows command prompt for it to run well. I'll copy the input cases that you see on the right now. Hopefully it'll work. Will it work? Come on, copy, paste. Why isn't it working? Oh my gosh, what's going on? Oh my god. Okay, what's going on? I will be back. Okay, I am back. I think my computer was lagging or something. So, let's run the code. Okay, it's not going to work right away. What the heck? Why isn't it working? Okay, it seems to be working now. Let me paste it in. And if I press enter, it should give us our answer. And the last number here is a 3, and that is the answer we are looking for. So hopefully, even though there are a lot of terminal errors here for some reason, this will work. So the solution, we are using C++14, I believe. Copy and paste our solution in here, and hopefully it will work when we submit it. My name is in fact Daniel, if you didn't know that. Compiling, and it is accepted. Let's go. I clearly didn't do this first try. I was also looking at my notes, so don't think that I am some genius or anything. It took me a really long time to solve this problem, and hopefully this video was helpful. Hopefully you tried solving this problem first before coming to this video. But if you did appreciate the solution, consider subscribing for more videos like this and giving it a smash of the like button if you did like the video. Thanks for watching, and I'll see you in the next video.